Have you ever stopped to think about what really exists between you and the nearest star? The so-called emptiness of space? That seemingly absolute blackness that separates the worlds? If you imagine that it's simply nothing, a perfect and complete vacuum where absolutely nothing exists, get ready, because the truth is going to turn your understanding of the cosmos upside down. And it all started when scientists realized that their equations were trying to say something deeply disturbing about the very nature of reality. Astrophysicist Neil deGrasse Tyson has a fascinating way of explaining this that will make you never look at the night sky the same way again. Because the space between the stars, that void that seems so empty, is actually buzzing with quantum activity so intense that if we could see with the right eyes, we would see a turbulent ocean of particles appearing and disappearing, fields intertwining, energies fluctuating on unimaginable scales. And this discovery is not just scientific curiosity, it is fundamentally connected to the greatest mysteries of the world. Universe, from the accelerated expansion of the cosmos to the very possibility of the existence of matter as we know it. Imagine for a moment that you could shrink in size, shrink to subatomic dimensions, and float in that supposed void between Earth and Alpha Centauri, the closest star to our solar system, which is approximately 4.3 light-years away. What would you expect to find during this journey through approximately 40 trillion kilometers of cosmic darkness? The answer will defy everything your intuition tells you is true, because contrary to what we can imagine by looking at space as this silent and dead place, the space vacuum is possibly the most living and dynamic thing that exists in the entire universe, constantly vibrating with activity at levels that our everyday perception could never capture. And if you are one of those who love to have your mind blown by scientific discoveries that completely redefine our understanding of reality, subscribe to the channel, because this journey through the void that is not empty will reveal secrets that connect on the smallest scale imaginable of quantum physics with the ultimate destiny of the entire observable cosmos. The history of our understanding of the vacuum is itself a fascinating journey through centuries of human thought, beginning way back in ancient Greece, when philosophers like Aristotle insisted that nature abhorred a vacuum, that there simply could not be a place where there was absolutely nothing. And this idea dominated Western thought for nearly 2,000 years, until in the 17th century, an Italian scientist named Evangelista Torricelli performed an ingenious experiment that would change everything. Torricelli took a glass tube closed at one end, filled it completely with mercury, and then inverted the tube into a basin also filled with mercury. And what happened was surprising. The mercury in the tube did not remain filled to the top, as would be expected if nature really hated vacuums. Instead, the level dropped, leaving an empty space at the top of the tube. And what Torricelli had created in the year 644 was the first artificial vacuum produced in laboratory, proving that yes, it was possible to have a space where apparently nothing existed. This experiment not only invented the barometer and helped us understand atmospheric pressure, it opened the door to a revolution in our understanding of the fundamental nature of reality, because for the first time in human history, we had concrete evidence that a vacuum could exist, that there could be places in the universe where there was no air, there was no visible matter. There was apparently nothing at all, and this discovery echoed throughout the following centuries as scientists began to develop better and better vacuum pumps, managing to create spaces with less and less air, fewer particles, getting closer and closer to what they imagined it to be, the perfect and absolute vacuum. In the 19th century, physics was confident that it understood the vacuum. It was simply the absence of everything, a space where there were no atoms, no molecules, no radiation, just pure nothingness waiting to be filled. But then something extraordinary happened that began to shake all this certainty. Scientists began to develop quantum mechanics in the early 20th century and discovered that on the smallest scales of reality, The rules that govern the behavior of matter and energy are completely different from the rules we observe in the everyday world, deeply strange and counterintuitive in ways that still challenge our imagination today. One of the fundamental principles of quantum mechanics is the Heisenberg uncertainty principle, formulated by Werner Heisenberg in 1927, which sets fundamental limits on how much we can simultaneously know about certain properties of a particle, such as its position and momentum. And this principle has an absolutely extraordinary consequence when applied to the vacuum itself, because it means that even in the emptiest possible space, even if you could remove every atom, every photon, every particle of matter and radiation, you still could not have a completely zero-energy state. You could not have absolute rest, because the very quantum nature of reality prohibits that. Think of it as if the universe has a fundamental unrest built into its most basic structure, an inability to be completely still even when we try to completely empty a patch of space. And this quantum vacuum unrest manifests itself in a way that seems straight out of science fiction, but is actually experimentally confirmed science, through something called quantum vacuum fluctuations, where particles literally appear out of nowhere, exist for infinitesimal fractions of a second, and then disappear again, temporarily violating the conservation of energy in a way that is only allowed by quantum mechanics due to another fundamental principle, the energy-time uncertainty relationship, which says that the shorter the time interval, the greater the uncertainty in energy can be, allowing for these momentary violations as long as everything resolves quickly enough. These particles that appear and disappear in the vacuum are called virtual particles, and although they exist for such brief periods that they cannot be detected directly, their effects are absolutely real and measurable, influencing virtually everything in the universe, from the mass of elementary particles to the structure of space-time itself. And this idea that the vacuum is teeming with pairs of particles and antiparticles constantly appearing and annihilating each other was developed by physicist Paul Dirac when he was working on an equation that described the behavior of electrons at high speeds, the famous Dirac equation formulated in 1928. Dirac realized that his equation had negative energy solutions that seemed to make no physical sense, and to explain this, he proposed something revolutionary, that all of space is filled with an infinite sea of negative energy electrons, what we now call the Dirac sea. And when one of these negative energy electrons receives enough energy, it can be promoted to a positive energy state, leaving behind a hole. And that hole would behave like a positively charged particle, thus predicting the existence of antimatter, specifically the positron, which was discovered experimentally by Carl Anderson just 4 years later in 1932, confirming Dirac's theoretical prediction in spectacular fashion. Although the modern interpretation is somewhat different from the original Dirac sea, the central idea remains valid. The vacuum is not an inert void, but rather a complex and dynamic quantum state, the lowest energy state possible, but definitely not a zero-energy state. And physicists call this residual energy that the vacuum possesses even when it is completely empty of matter and radiation, zero-point energy, the energy that exists at the absolute zero-point temperature, minus 273.15 degrees Celsius, where classically everything it should be completely still, but quantumly there is still movement, there is still fluctuation. There is still energy zigzagging through seemingly empty space. Now, you might be thinking that this all sounds very abstract and theoretical, just esoteric mathematics, with no real consequences in the physical world that we can observe. But here is where the story gets truly fascinating. Because there is direct and incontrovertible experimental proof that these vacuum fluctuations are absolutely real, something called the Casimir effect, which was theoretically predicted by Dutch physicist Hendrik Casimir in 1948 and confirmed experimentally for the first time in 1997 with extraordinary accuracy. The Casimir effect works like this. Imagine you take two perfectly flat and smooth metal plates and place them very close to each other in a vacuum, separated by a tiny distance of just a few nanometers. And what Casimir realized is that between these two plates, you restrict what types of quantum fluctuations can occur, because the waves from the virtual particles have to fit exactly into the space between the plates, so only certain wavelengths are allowed between them. Whereas on the outside of the plates, all wavelengths can exist freely. This creates an imbalance in the vacuum pressure. There is literally no more pressuring the plates from the outside than from the inside, because there are more types of quantum fluctuations happening in the external vacuum than in the restricted internal vacuum, and this imbalance generates a measurable force that pushes the plates against each other, the Casimir force, proving indisputably that the vacuum is not empty, but is full of real quantum activity that can exert physical forces on macroscopic objects. Let me tell you where you are watching this right now. Comment your city or country, because it is fascinating to think that it doesn't matter if you are in Brazil, Portugal, the United States, or anywhere on the planet. We are all immersed in this same quantum ocean of vacuum fluctuations that permeates not only outer space, but every cubic centimeter of the universe, including the air around you, at this very moment. And understanding this connects us in a profound way with the fundamental structure of the reality that surrounds us. Vacuum energy has even more extraordinary implications when we consider extreme astrophysical objects like black holes, because Stephen Hawking demonstrated in 1974 that quantum fluctuations of the vacuum near a black hole's event horizon can lead to an amazing phenomenon called Hawking radiation, where the black hole actually emits radiation and slowly loses mass over unimaginably long periods of time, eventually evaporating completely. The mechanism is subtle but profound. When a pair of virtual particles appears near the event horizon of the black hole, it can happen that one of the particles falls into the horizon while the other escapes to the outside, and to a distant observer, it appears that the black hole has emitted a real particle, and that escaping particle carries energy that must come from somewhere. Specifically, it comes from the mass of the black hole itself through Einstein's mass-energy equivalence. So the black hole gradually shrinks and evaporates, a process that for a stellar mass black hole would take much longer than the current age of the universe. But for microscopic black holes, it could happen relatively quickly. This means that even the darkest, emptiest object we can imagine, the interior of a black hole, is fundamentally connected to this quantum dance of the vacuum. And Hawking showed that the temperature of this radiation is inversely proportional to the mass of the black hole. So larger black holes are colder, while smaller black holes are hotter. And as a black hole evaporates and gets smaller, it gets hotter and hotter, emitting more and more intense radiation until it finally disappears in a final burst of radiation. Although this final process is still speculative because it involves physics that we don't understand completely, the union of quantum mechanics with general relativity remains one of the great unresolved challenges of modern theoretical physics. But there is yet another layer to this story about the vacuum that is not empty, something that permeates absolutely all space and is crucial to the very existence of matter as we know it, the Higgs field, discovered experimentally in 2012 at the Large Hadron Collider when physicists finally detected the Higgs particle, the Higgs boson, confirming a theoretical prediction that had been made there in 1964 by Peter Higgs and other physicists. The Higgs field is a fundamental quantum field that fills the entire universe, even the space we consider empty. And this field has an extraordinary property. It is not in its lowest energy state, when it has a zero value like most other fields. Instead, the lowest energy state of the Higgs field corresponds to it having a non-zero value everywhere, what physicists call the vacuum expectation value. And it is through interaction with this Higgs field permeating the vacuum that elementary particles, how electrons and quarks, acquire their masses. Think of the Higgs field as a kind of invisible molasses filling all space. Particles that interact strongly with this field are slowed down more intensely when moving through it, and therefore appear to us as having more mass. While particles that interact weakly with the Higgs field, or not at all like photons, are less affected and have less mass or no mass at all, and this means that the very mass of the particles that make up your body, the chair you are sitting in, the planet beneath your feet, is a direct consequence of the vacuum, is not really empty, but is filled with this Higgs field that permeates everything. So when Neil deGrasse Tyson talks about the vacuum not being empty, he is referring to multiple layers of reality that defy our everyday intuition. From microscopic quantum fluctuations to virtual particles arising and disappearing billions of times per second at every point in space, through zero-point energy that can never be completely removed, even in the most perfect vacuum, to fundamental fields like the Higgs field that fill the entire cosmos, giving mass to particles, and all of this is happening right now around you, in the seemingly empty space between you and the screen, between the Earth and the Moon, between the Sun and the most distant stars we can observe. But the story gets even more intriguing when we start looking at interstellar and intergalactic space on larger scales. Because even if there weren't all this fundamental quantum activity, the space between the stars still wouldn't be empty in the classical sense. It's filled with matter and radiation that are simply so diffuse that we can't easily perceive them, but which play crucial roles in cosmic evolution and the structure of the universe. Interstellar space, that region between the stars within a galaxy like our Milky Way, contains on average approximately 1 atom per cubic centimeter, and although this seems incredibly empty compared to the density of air, which has about 10 to the 19th power molecules per cubic centimeter, when you multiply that minuscule density by the absolutely colossal distances of interstellar space, you end up with immense amounts of matter. So much so that if you added up all the mass of gas and dust in the interstellar space of the Milky Way would reach approximately 10 billion times the mass of our Sun. A truly astronomical amount of matter floating in that supposed void. This interstellar gas is composed primarily of hydrogen, the most abundant element in the universe, along with approximately 25% helium and traces of heavier elements that were synthesized in the interiors of stars and spread throughout space when those stars exploded as supernovae. And this material is not just passively floating around. It actively participates in galactic evolution. Clouds of gas condense under gravity, forming new stars. Stars die and return chemically enriched material to the interstellar medium. Stellar winds and supernova explosions stir and heat this gas, creating complex and dynamic structures that we can observe through telescopes sensitive to different wavelengths. In addition to gas, interstellar space also contains tiny grains of cosmic dust, solid particles of compounds like silicates and carbon that formed in the atmospheres of evolved stars or were forged in stellar explosions. And although each individual grain is typically smaller than a micrometer in diameter, collectively they are responsible for absorbing and scattering starlight, creating the beautiful dark nebulae we see silhouetted against the bright backgrounds of star-forming regions. And these dust grains also serve as surfaces where complex molecules can form, including organic molecules that are precursors to life, suggesting that interstellar space may be a richer and more interesting chemical nursery than we previously imagined. And there is even more to this void that is not empty. Magnetic fields permeate interstellar space with typical intensities of approximately 1 microgauss, about 1/1,000,000th the intensity of the Earth's magnetic field, but extending over distances of hundreds or thousands of light years. These magnetic fields influence the movement of charged particles through the interstellar medium, shape the structures of gas clouds, and play crucial roles in processes such as star formation and the propagation of cosmic rays. which are particles of very high energy, mainly protons, traveling through space at speeds close to that of light, constantly bombarding the Earth's atmosphere and everything in space. And the energy density of these particles and fields is comparable to the energy density of starlight, or the turbulent movement of gas itself, showing that the interstellar medium is a complex and multifaceted energetic environment far removed from the simplistic image of a silent void. When we look at even larger scales, the intergalactic space between galaxies, the story becomes different, but equally fascinating. Because although the density of matter drops dramatically to something like 1 atom every few cubic meters of space, the distances are so immense that, again, you end up with colossal amounts of total mass. And this intergalactic gas is not evenly distributed, but organized into a large-scale structure called the cosmic web. Filaments of hot gas connecting clusters of galaxies through distances of tens or hundreds of millions of light-years. This intergalactic plasma is extremely hot, with temperatures in the range of millions of degrees Celsius, so hot that it emits mainly in X-rays, and it is only in the last few decades that we have developed sufficiently sensitive X-ray telescopes like Chandra and XMM Newton to actually map this hidden matter in intergalactic space, revealing that most of the ordinary baryonic matter in the universe, that matter made of protons and neutrons that makes up stars, planets, and our own bodies, is not actually in the stars or planets, but in this hot, diffuse gas permeating the space between the galaxies, called matter-missing baryonic acid, that astronomers had been searching for decades, and finally found hidden in that supposed void. And if all this quantum activity and all this diffuse matter weren't enough to fill the vacuum, there is the most mysterious and dominant component of all, something that Neil deGrasse Tyson and all modern cosmologists consider to be one of the greatest enigmas of contemporary science: dark energy, which constitutes approximately 68% of the entire mass-energy content of the universe, and is apparently evenly distributed throughout space, including what we call the void, causing the accelerated expansion of the cosmos that was discovered completely unexpectedly in 1998, when 2 independent groups of astronomers were studying distant supernovae. Researchers expected that the expansion of the universe was slowing down due to the gravitational pull of all the matter it contains, but to their complete surprise, they discovered that the expansion is actually accelerating. Distant galaxies are moving away from us faster and faster as time passes, and this could only happen if there was some form of negative pressure energy permeating all of space, an energy that has the opposite gravitational effect to that of normal matter, repelling rather than attracting. And this mysterious energy was called dark energy because we know absolutely nothing about its fundamental nature. In addition to its observational effects on the geometry and expansion of the universe, the simplest explanation for dark energy would be the cosmological constant, an intrinsic property of empty space itself, essentially a density of vacuum energy that remains constant as the universe expands, and this brings us back to the idea of quantum mechanical zero-point energy. Because you might think that dark energy is simply the large-scale cosmological manifestation of that residual energy that the quantum vacuum possesses, but here we encounter what is possibly the biggest disagreement between theory and observation in the entire history of physics, when you calculate how much the density should be. Of quantum vacuum energy using the tools of quantum field theory, you obtain a value that is approximately 10 to the power of 120 times greater than the observed value of dark energy, a discrepancy so absurdly large that it is difficult to even understand. And no one knows how to solve this problem that became known as the problem of the cosmological constant. This means that there is something deeply incomplete in our understanding of either quantum mechanics, gravitation, or both, and the true nature of the vacuum on cosmological scales remains one of the greatest unsolved mysteries of fundamental physics, connecting the smallest scale we can imagine. the quantum fluctuations of the vacuum with the largest observable scale, the accelerating expansion of the entire visible universe. So when we now look at that dark space between the stars, armed with all this scientific knowledge we have accumulated over centuries of careful investigation, we realize that it is absolutely teeming with fascinating phenomena operating on multiple scales simultaneously, from fundamental quantum fluctuations happening trillions of times per second at every infinitesimal point in space, to the Higgs field giving mass to particles, to interstellar and intergalactic gas, magnetic fields, cosmic rays, microwave background radiation. Left over from the Big Bang and permeating it all is the mysterious dark energy that determines the ultimate destiny of the entire cosmos. The void is not empty in any sense that our everyday intuition would suggest, and this revelation has practical implications beyond pure scientific fascination. Because if we are thinking about interstellar space travel, we need to understand that the space through which a ship would travel is not a benign vacuum, but a complex environment with radiation, high-energy particles, variable magnetic fields, and even very rare but extant particles of matter that at speeds close to that of light would become devastating projectiles capable of damaging any structure. And engineers need to consider how to protect crews and equipment against all forms of radiation and impact that exist in that seemingly empty space. Understanding the physics of the vacuum also has implications for emerging technologies, from potentially harnessing zero-point energy, although this remains highly speculative and probably impossible under our current understanding of the laws of thermodynamics, to the development of coatings and materials that minimize the Casimir force in nano-sized devices where this vacuum force could become significant, and the continued study of the properties of the quantum vacuum could eventually lead us to understand even more exotic phenomena, such as the theoretical possibility of multiple metastable vacuums in particle physics theories, raising fascinating and somewhat disturbing questions about the long-term stability of our own universal vacuum. Neil deGrasse Tyson often emphasizes in his presentations that science offers us not just facts and equations, but also a profound sense of wonder about the universe. And few scientific discoveries exemplify this better than the revelation that the vacuum is not empty, because it shows us that even when we try to imagine absolute nothingness, the universe conspires to fill that space with activity, with energy, with possibility, as if nature itself were horrified not just by the vacuum as Aristotle thought, but specifically by the inert, dead vacuum, insisting that every region of the space-time must vibrate with the fundamental quantum dance that characterizes reality at its most basic level. This completely changes our perspective on the cosmos because it reveals that there is no true separation between places where there are things and places where there is nothing. Everything is connected through this underlying quantum matrix. Every point in space is participating in this fundamental activity. And in some ways, this means that the universe is much denser, much richer, much more interesting than our everyday senses would suggest when we look up at the night sky and see mostly darkness. The philosophical implications are equally profound because they challenge our intuitive notion of existence and non-existence, suggesting that perhaps these categories are not as absolute as we think, that there is a gray area where quantum potentialities hover between being and non-being, where virtual particles exist in a very real sense despite their ephemeral existence, where fields permeate everything without being made of any tangible substance, but nevertheless exerting concrete influences on the material world. And when we consider that our own body, our own consciousness, arose from this universe governed by these same quantum laws, participating in this same cosmic dance between matter and energy, between existence and possibility, we gain a humbling but inspiring perspective on our place in this extraordinarily rich and complex cosmos. Not as separate observers looking at an inert universe out there, but as integral parts of this vibrant reality, literally made of the same enriched stellar material that floats in interstellar space, governed by the same quantum laws that make up the vacuum, buzzing with activity, connected through fundamental fields that permeate every cubic centimeter of observable space. If these revelations about the true nature of the vacuum of space have expanded your mind as much as mine, if you are fascinated by these discoveries that redefine our most basic understanding of what it means to exist in a quantum universe, please like this video, subscribe to the channel, and turn on notifications because we have many more deep explorations into the mysteries of the cosmos planned, from the nature of dark matter and energy to the paradoxes of quantum mechanics and the extreme limits of general relativity. Each video a unique journey to expand our understanding of the extraordinary universe we inhabit. The next time you look up at the night sky and see the darkness between the stars, remember that that apparent void is actually teeming with activity on scales ranging from the infinitesimally small to the cosmically large. That every point in that space is vibrating with quantum fluctuations, permeated by fundamental fields, shot through with cosmic rays and radiation, filled with traces of intergalactic matter, and dominated by the mysterious dark energy that guides the destiny of all that exists. And this realization does not diminish the sense of wonder, but amplifies it immensely, because it reveals that the universe is infinitely more sophisticated, more subtle, more surprising than our non-scientific imagination could ever conceive. Validating that famous phrase by astrophysicist JBS Haldane, who said that the universe is not only stranger than we suppose, but stranger than we can imagine, although science continues to expand the limits of what we can achieve. Let us assume, revelation after revelation, discovery after discovery, transforming the impossible of yesterday into the established knowledge of today, and opening new horizons of mystery for future generations to explore and unravel. And in this ongoing journey of discovery about the fundamental nature of reality, the revelation that the void is not empty remains one of the most profound and transformative insights we have ever achieved. A gateway to understanding that absolutely everything in the universe, including that which appears to be the purest nothingness, is vibrating with existence, with potentiality, with the eternal promise of that there is always more to discover, more to marvel at, more depths of reality waiting to be revealed by the curious eyes and inquisitive minds of those who dare to ask about the true nature of the cosmos that surrounds us and constitutes us at every conceivable level of existence.